Please subscribe this channel for educational videos and also don't forget to press the bell icon in order to get the instant notification of our latest stuff. Hello everyone. I welcome you all to this online course on network security. Our today's topic is IDEA, that is International Data Encryption Algorithm. So let's start this lecture. International Data Encryption Algorithm. The original name was IPES, that is Improved Proposed Encryption Standard. It was an improvement over the earlier algorithm, that is DES, Data Encryption Standard, and after its global acceptance, it was renamed as International Data Encryption Algorithm. It was developed by two researchers, namely Zoggia Lai and James L. Messi, in the year 1991 in Zuria, that is a place in Switzerland. They put this algorithm on the public forums, and till now, no cryptanalyst has come up with any of the weaknesses of this algorithm. Okay, IDEA is a symmetric block cipher like DES, and it operates on a 64-bit block of plain text. It does the encryption, and you will get a ciphertext block of 64-bit. Okay, as it is a symmetric block cipher, so on the both sides, either on the encryption as well as on the decryption side, you will use the identical keys. The key size in IDEA is 128-bit, and with this key, so far no weaknesses has been published by any of the cryptanalysts. Like DES, this IDEA algorithm works on rounds. So in certain books, it is written that there are 8 rounds with one extra round in the end, and other books write there are 70 rounds. Uh, and I will see that both the approaches are identical. Basically, in 8 round approach, what does it do is it generally clubs 2 rounds of this 17 round approach, and in the end they go for an extra round. So basically there are also 17 rounds, and that's why we will go with this 70 round approach in this lecture in order to understand the things. IDEA further uses a Mangler function. Mangler function takes certain inputs and does some operations, and then you will get uh, outputs according to those operations. What is Mangler function? We will see later in this lecture. But till now, you should be knowing that Mangler function is a non-reversible function. That is for decryption process. It runs in the same way as we used to do as we used to run it for the encryption process. Okay. One more thing with the idea is that it maps two 16-bit quantities into a single 16-bit quantity. That is when we go for operations like addition between two 16-bit quantities, or multiplication with two 16-bit quantities. It will give you a resultant, or it should give you a resultant of 16-bit. Okay. The three operations performed in IDEA are exclusive OR, that is bitwise exclusive OR, or you can say XOR operation. You must be aware about this operator. You must have studied this in number system or in digital logic design courses, and I know you people are aware about this operator. The next operation is addition, but it's not a simple addition, it's a modified addition. The resultant has to be 16-bit. So when we go for the addition, you have to throw out the carries, then only you will get a 16-bit result by adding the two 16-bit quantities. Okay, and that's why I am saying that it is a modified addition. Then you have third operation, that is called as modified multiplication, because it is not always possible when you multiply two 16-bit quantities and you will get a 16-bit result. So what is this modified multiplication? You first multiply to get a 32-bit quantity, and then find the remainder by taking the mod operation with 2 raised to 16 plus 1. Okay, that's what we call modified multiplication. So here we will see the general structure of this IDEA algorithm. So initially what you have in your hand is that is 64-bit input plain text, or 64-bit block of plain text. The approach in IDEA algorithm is that you first divide this 64-bit block into 4 blocks, and these 4 blocks are of 16-bit each. Okay, first you have this 64-bit block, of plain text, and then you will divide it into 4 blocks of plain text, and each block is of 16-bit. Okay, then you will feed this 4 block input to the round 1 like this. For the round 1, there are total 17 rounds, and to the round 1 you will give the 4 blocks input to the round 1. Okay, and this round 1 requires certain other inputs like keys. Okay, so we require the keys for this round 1, and as we know that IDEA uses a 128-bit long key, so out of this key IDEA will generate 52 different keys. Okay, because we have 17 rounds, and out of those 17 rounds we have 9 odd rounds and 8 even rounds. Okay, and each odd round will use 4 keys, and uh, even round will use 2 keys. Okay, odd rounds will use 4 keys and even rounds will use 2 keys, and in total we require 52 keys. And first of all, out of these 128-bit key we need to generate 52 keys, and each key will be 16-bit. Okay, so first of all, this 128-bit key will be expanded by using some key expansion algorithm, and then you will get 52 keys in total. And the first round, as it is an odd round, round 1, so we will require k1, k2, k3, k4, total 4 keys for the round 1. Okay, out of 52 keys. And then this round 1 will do certain operations, and you will get some output like this. The output will be again 4 blocks, and each blocks will be 16-bit. Okay, and this is what you call as your intermediate ciphertext. I will not say that this is your final ciphertext. This is what you call intermediate ciphertext, because this is going to be the input of next round. Fine, we'll see. Okay, this intermediate ciphertext will be the input to next round. This is round 2, and as it is round 2, we again require some keys for this round, and as it is even round, so we require 2 keys out of 52 keys. Okay, so these are the keys. K5 and K6 will be used for this round. Only 2 keys, because it is an even round. Fine. Again, after performing some operations in round 2, you will get some output, and this output will be again in the form of 4 blocks, and each block is of 16-bit. Fine. And similarly, you go on doing this, and you will reach at round 17. So again, round 17 will have input as 4 blocks of intermediate ciphertext, and again this will be given to the round 17. And the round 17, as it is an odd round, so again it will require the 4 keys, and these are the last 4 keys out of 52 keys. Okay, and again I'm telling you, all these keys right from k1 to k52, they are of 16-bit each. Okay, and then after performing some operations in round 17, there will be an output in the form of again 4 blocks. Okay, and each block is again 16-bit, and then these 4 blocks are concatenated to get a single block of ciphertext, 64-bit output ciphertext block, and this is what you call your final ciphertext block. Okay, this is the whole process and the basic general structure of IDEA algorithm. Now let's see the key expansion process in IDEA algorithm. So initially what you have 128-bit key, and that is expanded, that needs to be expanded into 52 keys, and each key should be of size 16-bit, and these are denoted as k1, k2 up to k52, and I'm again repeating here, each key is 16-bit. Fine. So initially you have 128-bit key, and you can divide this 128-bit key into 8 keys of 16-bit each. And then what you need to do is, if you want to generate k9 to k16, then you have to take a left circular shift of 24 bits. That is, the new key, that is the k9, will start at bit number 25. Okay, when you go for shifting towards the left side, and you will start your ninth key at bit number 25 and wrapping around to the beginning, then you will have uh, this kind of structure. Okay, the original key will be wrapped around again. Fine. And then you will start your ninth key at bit number 25 like this. Fine. You will have keys 9 to 16, and for other keys, that is, you have to offset 25 more bits and so forth until you reach the 52 keys, or until you generate the 52 keys. Fine. This is how the key generation works in IDEA algorithm. Okay. Rounds and 8 even rounds, and each round takes 64-bit quantity, that is your plain text, and that is treated as 4 16-bit quantities. Okay, 4 16-bit distinct quantities, and they are denoted as XA, XB, XC, and XT. Fine. These are the 4 16-bit quantities, and in total you have 64 bits. That is your first block of plain text. Then in the odd rounds, you use 4 keys out of the total key set, that is Ki, and these keys are denoted as Ka, Kb, Kc, and Kd. And similarly, you have even round, and where you use only 2 keys out of the total 52 key set, that is Ki, and these keys are denoted as Ke and Kf. And if you are using these keys, for example, for the round 1, that is odd round, and if for the round 1 these keys are K1, K2, K3, K4. Okay, these are for round 1. And when you talk about even round, and if it is a second round, that is round 2, then these keys are K5 and K6. So it is for round 2. And similarly, if we go on in the similar fashion, then for the round 3, the keys will be K7, K8, K9, and K10. And for the round 4, the keys will be K11 and K12. In the similar fashion, you can reach up to the round 17. Okay. Odd round description of IDEA algorithm. So initially you have 4 blocks of plain text as XA, XB, XC, and XT. And as it is an odd round, so you have 4 keys, and using those 4 keys and these 4 inputs, you have to apply some operations. And we first see that these are the operations that we will be performing in odd round. The first operation is multiplication, and the other operation is addition. So the addition and multiplication operations will be performed, and we use 4 keys for odd round as Ka, Kb, Kc, and Kd. And after performing these operations, that is multiplication and addition, you will get some result. Okay, and the resultant is again known as XA, XB, XC, and XT. As these XA, XB, XC are not similar to the previous XA, XB, XC, and XT, that's why I am showing these in the red color. Okay, but here you see the XA is replaced by XA multiplication with KA, and XD is replaced by multiplication of XD with KD. You can see from the diagram, XA is replaced by the multiplication of XA with KA, and XD is replaced by multiplication of XD with KD. And in the similar fashion, you see XC is replaced by XB plus KB. Okay, XC is replaced by XB plus KB, and XB is replaced by XC plus KC. XC plus KC, it will give you XB. Okay, and this XA, XB, XC, and XT that is shown in the red color, they are basically the new XA, XB, XC, XT, and you can say that these are the intermediate ciphertexts, and that you will apply as an input to the next round, that is the even round. Fine. The odd round is reversible in a sense that when we have to take the decryption process of this encryption process, in that case what we do is we take the multiplicative inverse of the keys, and then we take the mod with the 2 raised to the power 16 plus 1 entity. Okay, for more description of reversal of this first round, you can refer the book Charlie Kaufman and Mike Spencer's book on network security, because I have taken this lecture from that book. Okay, so this round, that is the odd round, can be reversible, can be decrypted by just taking the multiplicative inverse of the keys. Okay, now we will see the even round description. For the even round, again you have four input uh, blocks or four inputs of the plain text, that is XA, XB, XC, and XD. And it is a bit complicated as compared to with the odd round. Here we use another function that is called as Mangler function, and this Mangler function takes certain inputs. Okay, we will see there are four inputs to this Mangler function as Y in, Z in, KE, and KF. As this is an even round, these two inputs, that is KE and KF, these are the keys to this Mangler function. Okay, and these are the other inputs, that is Y in and Z in. So we can calculate Y in as XA XOR XB. Okay, the Y in is calculated by using this equation, that is XA XOR XB. So XA and XA XOR XB. So we can calculate Y in by doing this. And similarly, we have another input to this Mangler function, that is Z in, and it is calculated by using this equation, that is XC XOR XD. Fine. And then after performing some operations in the Mangler function, there will be outputs of this Mangler function, and these outputs are Y out and Z out. Okay, and what is Y out and what is Z out, we will see. Y out is equal to KE multiplication with Y in. Okay, KE is one of the keys, and Y in is the another input to the Mangler function that we have already calculated from this equation. Okay, then of this quantity we take the addition with Z in, that is another input to the Mangler function, and to this whole quantity we take the multiplication with KF. Okay, that is the another key. And similarly, you see the Z out is KE multiplied by Y in, that is one of the KE is one of the keys, and Y in is the one of the inputs to the Mangler function, and then this whole quantity will be added to the Y out, that we have already calculated through this Mangler function. Fine. And after that, after performing certain operation, you will get these entities XA, XB, XC, and XD as output of this particular round. These are the new XA, new XB, new XC, and new XD. Okay, and you can call it as intermediate ciphertext, because this will work as an input to the another round. Fine. And now we will see how this XA, XB, XC, and XD are calculated. And for XA, you have this equation XA XOR Y out. Okay, this is a new XA that is denoted here with the red color. XA is equal to XA XOR Y out. So we have to do this. You see, this new XA is equal to XA XOR Y out. Okay, and in the similar fashion, you will see XB, that is new XB, it is denoted by red color, and it is equal to XB XOR Y out. Fine. So we will see, we have to connect it like this. Similarly, you have new XC, that is this red colored new XC, it is XC XOR Z out, and we have to connect it like this. And then finally you have a new XT, which is equal to XD plus Z out. Okay, and from this equation you can connect this diagram in this manner. So this is all about the even round description of the this IDEA algorithm. This is how it works. Now, even around reversal, uh, as we saw in the this slide, that it is an encryption process, and if we go for the decryption process of even round, we have to go for the reversal of this round. And for that matter, we will see if new XA, new XB, new XC, and new XD are fed into even round, the output should be the old XA, XB, XC, and XD. That is for the decryption process. If we apply new XA, new XB, new XC, and new XD, you should get the result as old XA, XB, XC, and XD. For that, we see that the new XA is equal to XA XOR Y out, that you can see from the previous diagram. New XA is the operation of XOR between XA and Y out. It is very much clear from this diagram. Okay, and similarly, new XB is the XOR operation between XA and Y out. Fine. And then we saw in the beginning that XA XOR XB equal to YN, and that is the input to the Mangler function. And what if we use xa and new xb, new xa and new xb, then we will see new xa XOR new xb is equal to xa XOR y out XOR xa XOR y out, and which will give you xa and xb, that is your old xa and xb. This is how we applied the inputs to the Mangler function as new xa, new xb, and ultimately you will get the old xa and old xb for the same y in. Okay, and similarly you can do the same for xd and xd. By applying new xc and new xd, you will get the old xc and xd, because z in will be the will be same for xc and xd, and it is again same for the new xc and xd. You can practice it at your own, and if you need some more help, you can consult the network security book by Charlie Kaufman and Mike Spencer, because I have taken all this material from that book, and you can see how the reversal of the encryption process works, and either for even round or for odd round. So this is all what I had to show in this lecture. So hope to see you again. Thanks.